There's an adiabatic described. Any adiabatic process will subscribe to this relationship, just like the ideal gas law holds and the first law holds. So this is the law of an adiabatic process. And immediately you can see that P is proportional to 1 over V to the gamma power. And we've already argued that gamma always has to be larger than 1. So it agrees with our original conclusion, and that is that the adiabatic is more extreme than the isotherm. So now you've got the description of an adiabatic process. You've got the ability to calculate the work done in an adiabatic process because we have an expression for P as a function of V in an adiabatic. All you have to do is to know which gamma applies. If it happens to be a monatomic ideal gas gamma, it's simply 5/3. If it's something else, then it's something else. All right, now you want to talk about almost perfect timing. That's 1 minute left in class. How perfect is that? Questions, comments, cares, concerns?
My mind is blown.
Wow, that was...
You are wonderful people for coming on Friday like you did, so I'm going to do something special for you. I give you Monday off. Gift from me.
I think Martin Luther did that.
So, well, he was a good guy too. So remember, starting not next week, but the week after, we're going to go back to our original plan schedule. Monday afternoons will be our labs. I am now working out a schedule of laboratories so that you can know specifically what's going on when, but we'll talk about that next week. Are there any other questions? Yes?
Are we still going to have a double lecture on Mondays too?
No, what we're going to have is lecture Monday morning, lab Monday afternoon. We're going to go back to the traditional schedule that was published. So no, not a double lecture on Monday. We're just going to have to talk fast on Mondays and Wednesdays because there is no Friday lecture. Okay, that video camera may help a lot because I'll be talking faster and faster. But I shall be here on Friday mornings, and this room is available to us on Friday mornings. So Friday mornings, if you guys have questions or concerns about those fast lectures she was asking about, Friday morning will be the time. Come on in and we can talk about either the lecture or we can talk about homework problems. Okay, I got 2 more questions. Go ahead and then I'll get to you.
Can we still do what you're planning to do, which is just do labs whenever they come up, but do the Monday?
I'm going to try my best to fit them into the right place is what we're going to try to do on Monday afternoon. I'm going to try my best to do that. You had a question?
Yes, is this everything we'll be covering from chapter 19? Is this everything we'll cover from
This is everything we will cover in chapter. Yes, you notice, for example, there are some gray colored pages after this, which are sort of above and beyond the call of duty. And he adds those things in because I'm sure, if you keep this book, I'm sure in a year or so, those topics will be very useful to you in more advanced classes. So that was another thing our author did that I really appreciate. He just sticks these things on there and says, hey, this is coming in your future. So as far as we're concerned, we're going to do the stuff that's necessary and no more. And the gray pages are there to be useful to you later on. Anything else? All right. We've got to let the other class in here before they start getting ugly. So see you guys next Wednesday. Have a great weekend.
Howdy. I'm going to try and stick this on YouTube, actually.
So to get the new point, P2, you would take the original point and subtract the original volume and add the original temperature and subtract. So delta V, delta T represent the small changes in those 3 state variables. Now, also considering a small change in the internal energy, we're going to have du is equal to, and of course it would be d of m c sub v t, like that, but m and c sub v don't change, so du, the change in internal energy, is capital M c sub v dt. But what we're interested in is not specifically the change in internal energy, but indeed interested in the change in work, the amount of work done. So dW, which is what we're interested in, is going to be equal to this thing we're looking for, PdV. So there's that internal part of the integral, and we're just going to call it dW. So don't forget that Q equals 0. It's an adiabat. Adiabat. Okay, so by the first law, of course, first law, we would write du equals 0 minus dw, like that. And we have for du right here, mc sub v dt, mc sub v dt, and for minus dw, we have minus p dv. Okay. Our problem becomes finding p dv. Well, actually, that's easy to do, because I have now mixed up my notes. There. I'm back in order again. Put this one down, this one here. It's easy to get PdV if you recall that we simply can take the ideal gas law, which is PV equals NKT, and differentiate that law. What you end up with, of course, is D of PV equals D of NKT. Well, P of D of PV is, of course, P dV plus V dP equals, N and K are constant, so it's NK dt. Aha! This looks pretty darn good, doesn't it? Now we have an expression for dt. And I'll show you why that's so handy in just a second. It's just this divided by that. So, excuse me, PdV plus VdP over NK. And lo and behold, we can substitute that back into the first law. Where's the first law? Here it is, right here. So we can substitute it back into the first law. M C sub V dt equals minus P dV, and we can substitute this in right here. So, give me just a moment here, times, and this is P dV plus V dP divided by NK equals minus P dV. Substituting M equals NM, our first substitution, M equals NM. When we do that, of course, M C sub V times P dV plus V dP divided by K equals minus P dV. And of course, we've got terms in terms of dP and dV. So let's now collect the terms together. To do that, of course, we'll put this term over here, leave this term alone, and it might be handy now to first divide multiply both sides by K and divide both sides by MC sub V. So before we move terms around, let's just think of it as